All right. Well, this is a problem that's a dynamics problem. It says, what is the shortest time a race car can travel a quarter kilometer if the static coefficient of friction is 0.45 between the tires and the road? Well, let's write down what we're given. What is the shortest time? That's what we're looking for. So we'll say time equals question mark. And a race car can travel a quarter kilometer. A quarter kilometer is, in fact, delta D. And that's 0.25 kms, which happens to be 250 meters. We're also given the mu-s here. Static coefficient of friction is 0.45 between the tires and the road. But the one thing that we're not actually, we have to assume here, I can actually add it into the problem here, is we'll insert right in there, we'll say from rest. So in other words, we've got another condition here that says that our VI is 0. So how do we solve this? Well, first things first, let's actually find where these variables belong to. Delta T, or T, is a kinematics concept. Delta D is a kinematics concept. Mu, force of friction, is a dynamics concept. And VI is also a kinematics concept. That means this problem involves both kinematics and dynamics. Now, I want us to write down a very, very important sentence here, and that is that, in fact, the secret bridge, we'll put this kind of like in a little box here. Secret bridge between kinematics and dynamics is acceleration. So if you think of it as, let's say for example, if you think of it as the world over here of kinematics and the world over here of dynamics, the only thing that links these two worlds together is the bridge of acceleration. Okay? So that means let's begin this problem on the dynamic side over here. And the way I'm going to do that is I'm going to draw a free body diagram. Here's the road, and of course we assume level road. Here's the car, and the car is going to be accelerating in this direction, and we'll say therefore that's positive. Now that means there's going to be a few forces on it. Number one, let's use our magic sentence, what's touching it plus gravity? Well, the ground is touching it. The ground is going to have a normal force acting up. In addition, the ground is going to have a friction force acting on the car. Now, if you think about this, the car is accelerating, the person has just hit the gas pedal. The only thing that's going to move the car forwards is friction. If there was no friction, say for example if the car was on a very slippery, wet ice rink, then without friction the car cannot move forwards. So it is in fact friction that is causing the car to move forwards. So friction not only causes cars to accelerate, but it also causes cars to decelerate or come to a stop, depending on which direction it is. But in this case we're on the gas pedal. So those are the two forces that the ground exerts on the car. Let's finish the magic sentence. What's touching it plus gravity? And so there, of course, gravity is always down. Now that we've drawn our free body diagram, let's go to our first equation that we're going to use to solve this, and that is the summation of the forces is equal to F net. Now, we can actually apply this equation in two directions, one vertically and one horizontally. However, since we know that the car has no motion vertically, in other words, the car is not gaining altitude, it's not flying, so the car is staying on the road, that means there is no acceleration vertically, which means that the sum of the forces must equal 0 vertically. If that's true, that means that Fn has to equal mg. Why? Because they have to cancel each other out. The only way that the sum of the forces vertically could be 0 is if this force is equal and opposite to the gravity force. Okay? So that's where I get this from, Fn equals mg. Now, however, on the other hand, the sum of the forces does not equal 0 horizontally. What are they? Well, there's only one force horizontally, and it's FFR, and it's positive. So we'll say positive force of friction is equal to MA. Now, we can actually use another equation to simplify this even further. We have to substitute in what FFR is. And if we remember, force of friction equals mu Fn. Okay, so let's sub that in. But, interestingly, we now know what Fn is from here. So we can replace this with mu s mg equals ma. Now, you might think to yourself, where are we going with this? What are we trying to do? Well, if you remember earlier, I said that the bridge that we'd have to get from dynamics to kinematics is A. So what we're really looking for in this case is A. Thank goodness, because the masses cancel out, and that's very fortunate because I actually didn't provide the mass of this vehicle. But guess what? It doesn't matter, which means whether it's a small vehicle or a large vehicle, the answer isn't going to be any different. That's kind of neat to think about, if you will, because what that says is a small car or a large car does not have any inherent advantages here. However, if we now solve for this equation, obviously we get, oops, wrong color, we get mu sg equals A. We can now plug those values in. We know what mu s is. That was given in the problem. 0.45 times 9.8 meters per second squared, and that's going to give us our A. And what does that give us? Answer 4.41 meters per second squared. Well, so far so good, but at this point this now turns into a kinematics problem, because if you go back to the beginning of the problem, look what we have. We have T delta D, or actually we're looking for T, and we have delta D and we have VI. If you remember our kinematics equations, we have an equation that says delta D equals 1/2 AT squared plus VIT. This is perfect. This is the equation that we need. So we're going to be solving for T. Luckily for us, this term disappears since VI is 0. Therefore, we're just left with this T. Let's do a little bit of algebra and solve for t here. So we'll say t equals, take the 2 up top and take the a downstairs, 2 times delta d divided by a, and that's equal to t squared, but we don't want t squared, so we'll take the square root, and that should give us t. Now, if we plug in our values, what do we get? 2 times delta d, which was 250 meters, divided by an acceleration that we've already calculated, 4.41 meters per second squared. And if you work that through, you should get an answer of 10.65 seconds. And that's our answer. So I would say that's a pretty fast car. But if you'll notice, this whole problem was actually 2 problems in one. Okay? It doesn't look like it, but it is. We first solved a dynamics problem, and we found A, and then we were able to go to kinematics, and we used a kinematics problem or equation here, and we solved for t. Hope you enjoyed this problem. See you next time.